On July 9th, 2025, something happened to planet Earth that had never been recorded in the history of modern timekeeping. The planet completed one full rotation about 1.5 milliseconds faster than it was supposed to. That is not something you could ever feel. You could live 1,000 lifetimes and never notice a millisecond missing from a single day. But to the scientists watching the atomic clocks that track Earth's spin down to fractions of a heartbeat, that missing sliver of time was the loudest alarm bell in modern geophysics. Because 2 weeks later, on July 22nd, it happened again. And 2 weeks after that, on August 5th, it happened a third time. Earth was not having one strange day, it was accelerating. And it had been accelerating since 2020, breaking speed record after speed record with no agreed explanation. The researchers responsible for tracking the planet's rotation, geophysicists at institutions like the Scripps Institution of Oceanography and the International Earth Rotation and Reference System Service, were left holding a question that sounds almost absurd to ask about something as basic and reliable as a day. Why is Earth spinning faster? And right now, nobody, not one research team anywhere in the world, can give you a complete answer. If you're the kind of person who likes discovering that the most basic assumptions about our planet turn out to be genuine open mysteries, go ahead and subscribe. This channel covers the search for life beyond Earth and the strange, unresolved physics of the planet we already live on. And this is one of the strangest stories in either category, because it turns out the length of a single day may be tied directly to why life on Earth exists at all. Let's start with what a day actually is, because most of us have never had to think about it. Earth is defined as taking 24 hours, or 86,400 seconds, to complete one full spin relative to the Sun. Scientists call this the length of day, and they measure it using atomic clocks that split a second into billions of even smaller pieces. These clocks compare something called universal time, which is based on Earth's actual physical rotation, against international atomic time, which ticks forward with mechanical, unwavering precision no matter what the planet is doing. When Earth spins even a fraction slower than the atomic clocks expect, the length of day reads as a positive number of milliseconds. When Earth spins faster, it reads as negative. For most of recorded history, that number has trended positive. Earth has been slowing down, gradually, for billions of years, mostly because of drag from the moon's gravity acting on our oceans. That slowdown is not fast. It adds up to only a couple of milliseconds per century, but it has always been the expected direction: slower, longer days, a predictable, almost boring trend line. Then 2020 arrived, and the trend line broke. That year, Earth recorded 28 of the shortest days ever measured since the atomic clock era began. Scientists initially assumed it was a blip, the kind of short-term wobble Earth's rotation is known to have. But the wobble did not correct itself. In 2021, the acceleration continued, and for the first time, researchers began seriously discussing the possibility of a negative leap second, something that had never been implemented in the entire history of global timekeeping. In 2022, Earth broke its own record again, spinning through June 29th, 1.59 milliseconds faster than the standard day. In 2023, the speedup became so consistent that it actually shifted the calculated path of a solar eclipse compared to projections made decades earlier. Then came July 5th, 2024, when Earth completed a rotation 1.66 milliseconds faster than 24 hours, a new all-time record. And 2025 delivered an entire cluster of record-breaking days in a single summer: July 9th, July 22nd, August 5th, each one among the fastest rotations ever measured with modern instruments. Leonid Zotov, one of the leading researchers on Earth's rotation at Moscow State University, put it about as plainly as a scientist ever puts anything: nobody expected this. Here is where the story gets genuinely strange, because you would think a mystery this consistent would eventually resolve itself into a clean cause. It has not. Instead, when researchers went looking for an explanation, they found not one suspect, but several, all pulling on Earth's rotation in different directions at the same time, some speeding it up, some slowing it down, layered on top of each other like competing signals in radio static. Untangling them has become one of the more genuinely open problems in modern Earth science. The first suspect is the most obvious one, and also the most misleading. It's the moon. For billions of years, the moon has been the single biggest reason Earth's rotation slows down at all. Its gravity pulls on our oceans, creating tidal bulges that drag against the solid Earth as the planet spins beneath them, like a brake pad rubbing against a wheel. This tidal friction is why the moon is also slowly retreating from us, drifting outward by about 3.5 centimeters every year, roughly the speed your fingernails grow. As the moon steals a tiny bit of Earth's rotational energy, It converts that energy into higher orbital altitude for itself, and Earth's spin very gradually loses momentum in return. So on paper, more moon influence should mean a slower Earth, not a faster one. But researchers noticed something curious about the recent record-breaking days. Several of them landed on dates when the moon was near its maximum distance from Earth's equator in its orbital tilt. At that particular geometry, the moon's tidal pull on Earth's solid body, not just the oceans, briefly nudges the whole planet to spin a little quicker rather than slower. It is a small, short-lived effect, and on its own, it cannot explain a 5-year acceleration trend. But it does explain why certain days specifically are the record breakers, layered on top of whatever the deeper, longer-running cause turns out to be. The second suspect lives about 1,800 miles beneath your feet, inside a ball of solid iron roughly the size of Pluto, spinning in near isolation, cushioned from the rest of the planet by an ocean of liquid metal. Earth's inner core is not rigidly locked to the mantle and crust above it. Because it floats inside the liquid outer core, it can rotate at its own pace, sometimes a little faster than the rest of the planet, sometimes a little slower, and the two layers exchange angular momentum back and forth the way a figure skater's arms and torso exchange momentum during a spin. When one part speeds up, the other tends to slow down to compensate, and vice versa. In 2023, seismologists at Peking University, Yi Yang and Xiaodong Song, published a study using decades of seismic wave data from repeating earthquakes, essentially using the shock waves from real quakes as a kind of sonar to time how fast the inner core was rotating relative to everything around it. What they found was that the inner core's rotation appeared to pause around 2009 and then begin turning backward relative to the mantle sometime in the years since, part of what looks like a roughly 70-year oscillation, with a previous turning point back in the early 1970s, because the inner core is gravitationally coupled to the mantle and magnetically coupled to the churning liquid outer core that generates Earth's magnetic field. A shift in how the inner core spins does not stay contained down there. It ripples outward, subtly changing how fast the solid Earth around it spins, and even showing up in small, measurable disturbances in the planet's magnetic field itself. Not every researcher agrees on the exact size or timing of this effect, and the debate over exactly how the inner core moves has been running for over 20 years. But the timing lines up suspiciously well with the acceleration we have been watching since 2020. The third suspect is working in the exact opposite direction, and it is the one that made international headlines when a geophysicist named Duncan Agnew published his findings in the journal Nature in March of 2024. Agnew was not studying Earth's rotation to solve a mystery about speed. He was trying to figure out when the world would need its first ever negative leap second, a correction to global clocks that has never once been applied in the history of timekeeping. What he found was that global warming is now measurably slowing Earth's rotation down, and doing it by redistributing the planet's mass. As ice sheets in Greenland and Antarctica melt, the water does not just disappear, it flows into the oceans and spreads out toward the equator, shifting Earth's mass away from the poles and toward the planet's widest point. Picture a figure skater again, this time pulling her arms in to spin faster or stretching them out to slow down. Melting polar ice is Earth stretching its arms outward, and it measurably drags the planet's spin down in response. Agnew calculated that this ice melt effect has been large enough to delay the need for a negative leap second by roughly 3 years. Without global warming's influence on Earth's mass distribution, timekeepers might have needed to subtract a second from global clocks as early as 2026. Instead, current projections point to somewhere around 2028 or 2029, an estimate Agnew himself describes as genuinely uncertain. It is a strange kind of headline. Global warming, in this one narrow and almost accidental sense, is currently working against the acceleration coming from deep inside the planet, not toward it, buying timekeepers a few extra years to figure out what to do about a problem that has literally never existed before. There is also a slower, older version of this same mass redistribution effect still playing out from the last ice age. Large parts of the high-latitude northern hemisphere are still physically rebounding upward after being crushed under miles of glacial ice that melted away roughly 12,000 years ago, a process called glacial isostatic adjustment. Land that was pressed down for tens of thousands of years is still slowly rising, millimeters at a time, and that ongoing rebalancing of Earth's shape adds yet another layer of long-term influence on the planet's spin, separate from and much slower than what is happening with today's melting ice. The fourth suspect is the air above you and the water around you, both of which are constantly exchanging angular momentum with the solid ground beneath them. Wind patterns, ocean currents, and large-scale climate cycles like El Niño all shift enormous amounts of moving mass around the planet's surface, and every one of those shifts has a tiny reciprocal effect on how fast the solid Earth spins. In the same way a passenger walking toward the front of a canoe changes how the canoe sits in the water. Layered on top of that is something called the Chandler Wobble, a roughly 14-month cycle in which Earth's actual geographic poles trace a small irregular circle across the planet's surface. Only a few meters wide, but wide enough to subtly influence the length of day measurements scientists are trying to interpret. None of these atmospheric and oceanic effects are large enough on their own to explain a 5-year global acceleration trend, but they add noise on top of signal, which is part of why isolating the true underlying cause has been so difficult. So, where does that leave the mystery? In 2026, the data has thrown one more curveball. After 5 straight years of record-breaking speed, this year's short days have been noticeably less extreme than 2025's, with the shortest projected day of the year measuring roughly half a millisecond faster than standard, compared to more than a full millisecond the year before. That could mean the current acceleration episode is beginning to fade. It could also mean nothing at all, a temporary lull inside a longer pattern that will spike again next year. Nobody currently studying Earth's rotation is willing to commit to which one it is, and that uncertainty is itself the honest state of the science. Multiple real, physically distinct forces, lunar geometry, inner core oscillation, melting ice, glacial rebound, atmospheric and oceanic momentum exchange are all acting on the same spinning planet at the same time, some speeding it up and some slowing it down. And right now, researchers cannot fully separate which force is responsible for how much of what we are seeing. This is not just an academic curiosity either. It has real consequences for how modern civilization keeps time. Since 1972, the world has periodically added leap seconds to keep our clocks synced with Earth's actual slightly irregular rotation, tacking an extra second onto a specific day whenever the two started drifting too far apart. The last one was added at the end of December 2016. Every leap second added so far has been a positive one, stretching a particular minute to 61 seconds, because Earth has always eventually been the slower party in the relationship. A negative leap second would be something genuinely unprecedented, deleting a second from global time entirely, and nobody knows exactly what that would do to the vast, tangled infrastructure of computer systems, satellite navigation networks, and financial trading platforms that assume time only ever moves in one direction, second by second without gaps. Positive leap seconds alone have caused real technical chaos in the past, including outages at major internet platforms when systems fail to handle an extra second gracefully. A negative leap second, subtracting time nobody has ever subtracted before, is considered by the people who manage global timekeeping to be a genuinely higher risk event. For now, the International Earth Rotation and Reference System Service has confirmed there will be no leap second added in the near term, since Earth is currently running fast rather than slow. But the broader question of when, or whether, we will need to remove a second from human time for the first time in history remains unresolved. Now step back from the last 5 years entirely, because the truly strange part of this story is not what is happening to Earth's rotation right now. It's what has been happening to it for billions of years, and how directly tied that ancient history is to the reason you exist at all to watch this. When the moon formed, most likely from a Mars-sized object slamming into the young Earth around 4.5 billion years ago, our planet was spinning dramatically faster than it does today, with some models suggesting early days may have lasted only a handful of hours. Since then, tidal friction from the moon has been acting as a very slow brake, stretching those short early days out longer and longer across deep time. But that slowdown was not a smooth, uninterrupted line. Geologists using a technique called cyclostratigraphy, which reads faint rhythmic layers preserved in ancient sedimentary rock, the way you might read growth rings in a tree, discovered something unexpected a few years ago. Between roughly 2 billion and 1 billion years ago, Earth's day length appears to have gotten stuck, flatlining at close to 19 hours for an entire billion-year stretch. Geologists sometimes nickname the boring billion, a period known for slow biological change and unusually stable environmental conditions. Researcher Ross Mitchell and colleagues proposed that Earth had entered a kind of tidal resonance during that period, where the ocean tides pulling the planet's spin down were, for a while, almost perfectly balanced by an opposing atmospheric tide, driven by solar heating gently pushing the spin back up. For nearly a billion years, those two forces canceled each other out, and Earth's day length simply stopped changing. Here is where this connects directly to the reason any of this matters for the search for life. Because day length was not just a background detail during those billions of years. According to a striking body of research led by geomicrobiologist Judith Klatt and colleagues, day length may have directly controlled when complex life became possible on this planet at all. The researchers studied modern microbial mats living at the bottom of the Middle Island sinkhole in Lake Huron, a strange, sunless, sulfur-rich environment considered one of the closest living analogs we have to conditions on early Earth, billions of years before animals, before plants, before anything with lungs or leaves. In these mats, purple, oxygen-producing cyanobacteria compete for space with white, sulfur-eating bacteria, and the two groups essentially take turns controlling the surface of the mat depending on the time of day. At night, the white sulfur bacteria rise to the top. When morning light returns, the purple cyanobacteria push upward to reclaim the surface and begin photosynthesizing. But that transition is not instant. There is a long lag every morning before the cyanobacteria really get going and start pumping out meaningful amounts of oxygen. Klatt realized that this lag creates a hard limit on how much oxygen a short day can produce, no matter how bright the sun is. On a short day, the useful highlight window closes before the mat can build up much of an oxygen surplus. On a longer day, that same mat has hours more time to keep releasing oxygen before nightfall resets the whole cycle. When Klatt's team modeled this effect across Earth's entire rotational history, applying it globally instead of just to one lake, the pattern that emerged lined up strikingly well with the actual, real, geologically documented history of Earth's atmospheric oxygen. Oxygen did not rise on Earth in one smooth increase. It rose in two dramatic steps, separated by an enormous stretch of relatively low, stagnant oxygen levels in between, the very same boring billion where day length had stalled. The first oxygen surge, the Great Oxidation Event, happened roughly 2.4 billion years ago. The second, called the Neoproterozoic Oxygenation Event, happened far later, somewhere between 800 and 540 million years ago, right as day length was finally breaking free of its billion-year plateau and beginning to stretch out again. According to this research, those were not coincidences. As Earth's day length increased, each cyanobacterial mat gained more usable daylight hours per cycle, released more surplus oxygen into the water and the air, and pushed atmospheric oxygen levels a little higher in step. The rise of breathable air on this planet, the very foundation that eventually made animal life and human life possible at all, may be tied directly to how fast or slow the planet happened to be spinning at the time. Which brings the story all the way back around to why any of this belongs in a conversation about the search for life beyond Earth. Because if day length genuinely gated the timing of Earth's own oxygenation, then rotation rate is not just a curiosity we track with atomic clocks. It may be one of the hidden variables that determines whether a planet elsewhere in the galaxy ever gets the chance to build a breathable atmosphere at all. Most of the exoplanets currently considered our best candidates for habitability orbit small, dim red dwarf stars, simply because those planets are easier to detect, and their habitable zones sit close enough to study in detail. But planets orbiting that close to their star are frequently tidally locked, meaning one side permanently faces the star in perpetual daylight, while the other side sits in permanent darkness, with no day-night cycle at all in the way Earth has always had one. Researchers studying exoplanet habitability have begun proposing something they call a photosynthetic habitable zone, a region defined not just by whether liquid water could exist, but by whether a planet's rotational behavior would even allow the kind of oxygen buildup that made Earth's atmosphere breathable in the first place. A planet could sit comfortably inside the traditional habitable zone, have oceans, have the right temperature, have every ingredient chemistry requires, and still never develop the kind of atmosphere we would recognize as a biosignature, simply because its spin state never gave photosynthetic life the rhythmic light and dark cycle it apparently needed here. That is the quiet, genuinely strange thread running underneath everything happening to Earth's rotation right now. The same planet currently confusing geophysicists with unexplained speed records, the same planet whose spinning core, melting ice, and shifting oceans are all tugging its day length in different directions at once, spent billions of years slowly, unevenly lengthening its days in a way that appears to have directly built the air currently in your lungs. We are still inside that same dynamic system. Earth's rotation has never been fixed, never been simple, and never fully belonged to any single cause. It is being pulled at by the moon, wrestled with by its own core, nudged by melting ice at the poles, and stirred by the atmosphere and oceans moving overhead, all at once, all the time, and it has been that way for 4.5 billion years. When we go looking for life on other worlds, we tend to ask the same short list of questions. Is there water? Is there the right temperature? Is there an atmosphere? Earth's own deep history suggests we may need to start asking one more question just as seriously. How fast or how slowly is that other world actually spinning, and for how long has it been doing it? Because on this planet, that answer may be the reason there was ever anyone here to ask the question at all.